Hello everyone, so in this lecture I'm gonna talk about the Dirac delta distribution. So this is the first part of three videos in fact, in which I will start with the definition of the Dirac delta function or Dirac delta distribution in fact. And the final objective is to define the Fourier integral. So I will start to talk about the Dirac delta distribution and I will arrive to the Fourier integrals and how we define the Fourier integrals of a function. So this is the subject of the next video. So in this video I will talk about the Dirac delta distribution, or in a wrong way, the Dirac delta function. So the delta is not a function, is a distribution, because of the fact that there is not a unique way to represent it in fact. So first of all, how this function is defined in fact. So if any function satisfies simultaneously these two conditions, so the first condition is that the limit of the function when x tends to a certain point x0, this limit should be plus infinity, and at the same time the integral from minus infinity to plus infinity of our function should be equal to 1. And when fx satisfies both of these equations, both of these conditions, in fact f of x is exactly delta of x minus x0. So the Dirac delta function, or not really a function, but we will call it wrongly the Dirac delta function, at a point around the point x0, or delta index x0 of x. Both of these notations are used in the literature. So if I plot a typical Dirac delta function around the point x0, in fact the function should go to infinity at this point, such that its integral from minus infinity to plus infinity, this area under this curve, in fact the curve of f of x, the area should be unity. So in this case f of x is exactly delta of x minus x0. So I will start with giving different representations of a Dirac delta function. So if I take into consideration this constraint, as you remember, this constraint is in fact the condition for any probability distribution function. As you remember, the integral of any probability distribution function is equal to 1. But this condition has nothing to do with that, with the condition of the probability distribution function. But if I consider also that f of x is a positive function, so f of x is positive, using these two conditions, I can say that f of x can be imagined as a probability distribution function. So in order to give you some different examples of the Dirac delta function, I will start with the first representation, which is called the rectangle function, or the uniform probability distribution function, or the uniform random variable in fact. So as you remember, if I consider a random variable x following a uniform distribution within the interval a to b, the probability distribution function, the probability density function in fact of x, is equal to the inverse of the length of this distance in fact, when x belongs to the interval a to b, and otherwise it should be 0. So from a to b, the value of the function is 1 over b minus a, and it's 0 otherwise. So in this case, the area is equal to 1. So I will consider another similar function of x0 and sigma, and I will define this function, in fact, like this. So f of x0 and sigma is centered around x0 as we wish, in fact, here. And the radius around x0 is sigma. So this is x0 minus sigma, this is x0 plus sigma, such that this interval, this distance is 2 sigma. So the value of the function, in fact, is 1 over 2 sigma. So the function 1 over 2 sigma and 0 when x is between x0 minus sigma and x0 plus sigma, and it's 0 otherwise. So as we see, the area under this curve is always equal to 1 because of the fact that f is a probability distribution function. But if this sigma tends to 0, what happens for this function? So I will observe that the function changes. For example, if I use some smaller value for sigma, this interval will be smaller and the height will be larger. So this is the same function but for a smaller value of sigma. And at the end, when sigma tends really to 0, I will have a function such this one, like this function. In fact, the interval around the point x0 tends to 0, and this height tends to infinity. And again, the area under this function is always equal to 1, independent of the value of sigma, in fact. So this function can be imagined as this limit function is exactly one type of the Dirac delta function. So I can say that from one side, the limit of this f of x0 and sigma, when sigma tends to 0, is plus infinity, and the integral over r of f of x dx, f of x0 and sigma dx, is always equal to 1. So hence we can say that f of x0 and sigma, when sigma tends to 0, is exactly the Dirac delta function around the point centered at x0. So now, before going to the second, this is the first representation of a Dirac delta distribution. Now, before going to the second representation, I will give you one of the most important theorems when it comes to the Dirac delta function. So this theorem, in fact, states that if I integrate any arbitrary function, well-behaved function g of x, times the delta of x minus x0, and if I do this integration, if I carry out this integration from minus infinity to plus infinity, this is equal to the value of our function at this point, g of x0. So how we can prove? In fact, I will prove this theorem in a special case of the rectangle representation, rectangle function for the Dirac delta distribution. So if this delta is exactly this f of x0 and sigma, I can write this integral. In fact, I can decompose this integral as, in fact, because of the fact that this delta, which is considered to be f of x0 and sigma, defined here, in fact, is the limit, in fact we will consider is the limit in fact of this f of x0 when sigma tends to 0, I will have the limit of the integral from minus infinity to x0 minus sigma of g of x times f of x0 sigma d of x, plus limit from x0 minus sigma to x0 plus sigma of g of x times f of x0 and sigma d of x, plus the limit from x0 plus sigma to the plus infinity of g of x, f of x0 sigma d of x. And due to the fact that this f x0 sigma, in fact all these limits are when sigma goes to 0. And I know that this f as defined here is exactly, in fact vanishes when x doesn't belong to this interval. So this and this integral will be simplified, will be 0, such that the final result, in fact now in this interval, in fact I can replace the value of the f x0 sigma as 1 over 2 sigma. So the final result of this integral is the limit of the integral from x0 minus sigma to x0 plus sigma of g of x dx divided by 2 sigma when sigma tends to 0. So I can approximate this integral because of the fact that when sigma tends to 0, the interval of integration tends to 0 also, tends to a point x0, so that I can consider this integral approximately as the value of the function evaluated at the centered point x0 times the interval of integration divided by 2 sigma, and the final result is g of x0. Here there is some limit when sigma tends to 0, so that this theorem is shown. But in the special case of delta represented as a rectangle function. So now I will give you another representation of a Dirac delta function. So this is one of the most famous functions in the probability and statistics, which is called the Gaussian function. So the Gaussian or normal distribution. So as you remember, if I consider a random variable x following a normal or a Gaussian distribution with parameters x0 and sigma, so this is the mean value, this is the standard deviation, I know that f of x0 and sigma, f of x in fact, so the probability distribution function of the variable x indexed by these, parameterized by these two parameters, is equal to 1 over sigma square root of 2 pi times the exponential of minus x0 squared divided by 2 sigma squared, and x belongs to the real values. If I plot this function, as you remember, I have a symmetrical shape around the point x0, around the mean value. And if you remember, if I consider, in fact, if I take 2 times the derivative of this function and I solve the equation, f double derivative of f equal to 0, I can calculate these 2 points of inflection which are respectively x0 minus sigma and x0 plus sigma. So that the majority of data in the normal distribution, as you remember, belong to the interval of mean minus a standard deviation to mean plus a standard deviation. So this interval as a result is equal to 2 sigma. And this height, in fact, the maximum height, is simply equal to 1 over sigma square root of 2 pi. And the limit behavior of this function, if I use smaller and smaller values for sigma, I will have something like this. So from one side, the interval, this interval is decreased, in fact, because sigma is decreased. And this height will be increased because sigma is going to be smaller and smaller. And at the end, in a limit sense, in fact, I will have a function like this one. So this is the limit of this f of x0 on sigma when sigma tends to 0. So from one side, I can say that the limit of f of x0 on sigma when sigma tends to 0, the limit at this point is equal to the plus infinity, and the integral from minus infinity to plus infinity of f of x0 on sigma dx, as we know that this function is a probability distribution function, we know that for any pair of the values for x0 on sigma, this integral is always valid, so that the f of x0 on sigma when sigma tends to 0 is exactly another Dirac delta function. So we are seeing that we can represent a Dirac delta function with using different functions. And the last representation that I will present in this video, in this first video in fact, is a Cauchy distribution. So as you remember, if x follows a Cauchy distribution with parameters x0 and sigma, the probability distribution function of x is equal to sigma over pi divided by x minus x0 squared plus sigma squared. The plot of this function is way similar to the plot of the normal distribution, and we can do the same observation. So around the point x0 we will have something like this, with a height of 1 over sigma pi. If x is equal to x0, this quantity is 1 over sigma pi, and when this sigma tends to 0, the height tends to infinity, to the plus infinity. However, the area under the curve remains always equal to 1, and this these two conditions are satisfied, and we can say that f, in fact this is f of x0 and sigma. This f of x0 and sigma when sigma tends to 0 is again another representation for the Dirac delta function. So in this lecture I've presented three different functions for the representation of a Dirac delta function. So this is the result, this is the reason why the Dirac delta is not a function and it's a distribution. And also I've shown one of the most important properties of the Dirac delta function, which states that the integral of the Dirac delta function, sorry, this is here, of it, the integral from minus infinity to plus infinity of it, the Dirac delta function around the point x0 times any function, the result is the value of the function evaluated at this point. Sorry. So in the next video I will give another example, another function to represent the Dirac delta function, which is not a positive function. Now I will use a negative function. Thank you very much.